January 16th, 1942, 12:01 a.m., off New York. A German submarine is running on the surface near the American coast when an aircraft suddenly appears overhead and drops 4 bombs. In theory, this should have been the end of the mission. A large U-boat, thousands of miles from its base in occupied France, had no business operating this close to New York, let alone surviving after being spotted from the air. That was the expectation. The United States had entered the war only weeks earlier. Distance still seemed like protection. The Atlantic itself looked like a defensive wall. And yet, German submarines were already punching through it. But what almost nobody on the American coast understood that night was this: Germany had not sent just any submarine. It had sent a Type 9B, a long-range ocean raider designed for a completely different kind of war. A boat built to cross the Atlantic, attack repeatedly, evade when necessary, and still have enough fuel, power, and structural strength to make the return voyage. The engineering challenge behind that machine was enormous. How do you build a submarine that can carry 22 torpedoes, support a crew of 48 to 56 men, travel 12,000 nautical miles at 10 knots, and still dive deep enough to survive combat damage and depth charge pursuit? How do you fit all of that inside a hull only 76.5 meters long without turning it into a slow, helpless target? This is the story of the Type 9B's secret. How German engineers built the submarine that brought the war to the American coastline, and how its design exposed a hidden truth about naval warfare in 1942. Sometimes the decisive weapon is not the one with the biggest gun. It is the one that can get there at all. To understand why the Type 9 mattered, you need to understand the geography of the war. Germany could not defeat Britain directly at sea in a classic fleet battle. The Royal Navy was too large and the oceans were too wide. But Britain survived on imported food, fuel, raw materials, and military supplies. If those merchant ships stopped arriving, Britain would choke. That was Karl Dunitz's central idea: attack the shipping, not the symbol of British power, but the machinery of British survival. The problem was range. German bases on the Atlantic coast of occupied France, especially Lorient, were far from the American East Coast. A submarine sent to U.S. waters had to survive a full Atlantic crossing before it could even begin hunting. Then it needed to stay on station long enough to make that voyage worthwhile. Then it had to come home. That meant Germany needed more than a short-range ambush boat. It needed a transoceanic attacker. The answer was the Type 9 family, designed in 1935-36 as a large ocean-going U-boat derived from the earlier Type 1A. The original Type 9 already offered much greater endurance than many smaller boats. The improved Type 9B extended that endurance further. Later, the Type 9C added even more fuel capacity, pushing the class deeper into true long-range warfare. Think of it like the difference between a coastal patrol aircraft and a strategic bomber. Both can attack, but only one is designed to travel to a distant target, operate there, and still come back under its own power. That mattered in early 1942 because the American coast was dangerously exposed. The East Coast had not been fully blacked out. Coastal towns were brightly lit. Merchant ships often sailed independently. Navigation lights still burned. In some cases, ships transmitted their positions openly. German crews later described the scene as looking almost like peacetime. So when Dönitz launched Operation Paukenschlag, he was not just exploiting weak defenses, he was exploiting them with exactly the right machine. He wanted 12 boats. Hitler allowed 6. Mechanical trouble reduced the operational attack force to 5.
And yet those 5 boats sank 25 ships, totaling 156,939 tons in January 1942 alone. That is the historical shock. But the deeper story is not just that America was unprepared. It is that German engineers had already solved the problem of how to project submarine warfare across an ocean.
The Type IXB existed because submarine design in the 1930s was a series of brutal trade-offs. If you want more range, you need more fuel. If you want more fuel, you need more hull volume. If you want more hull volume, the submarine gets bigger. And once it gets bigger, it becomes harder to hide. That was the problem German designers had to solve. 1. Range. The original Type IX had a surfaced range of 10,500 nautical miles at 10 knots. That was already substantial. But the Type IXB improved that by 1,500 nautical miles, reaching 12,000 nautical miles at 10 knots. That increase was not just a nice bonus, it was the difference between being able to cross the Atlantic and patrol, or crossing the Atlantic and immediately worrying about the fuel needed to get home. 2. Payload. A long-range patrol boat without a heavy weapon load is a waste of distance. The Type IX family used 6 torpedo tubes, 4 in the bow and 2 in the stern, and carried 22 torpedoes. It could also carry mines in some configurations, though many boats were used mainly as torpedo attackers. That heavy load gave commanders something smaller submarines often lacked: endurance with striking power. Imagine building a truck capable of driving across a continent, then loading it with only a few crates. The distance becomes meaningless if the payload is too small. The same rule applies at sea. 3. Crew and habitability. A long-range U-boat was not just a weapons platform. It was a floating system for keeping dozens of men alive and functional over weeks at sea. The Type IXB carried a crew of 48 to 56 men. That required food storage, battery space, torpedo storage, fresh water management, ventilation, spare parts, and crew berthing, all inside a narrow steel cylinder. This is where submarine design becomes less like shipbuilding and more like mechanical compression. Every meter mattered. 4. Power. On the surface, the Type IX boats used diesel power. Underwater, they switched to electric motors fed by batteries. For the IXB and IXC technical summaries, total output is given as 4,400 horsepower surfaced and 1,000 horsepower submerged. Post-war technical studies of the IXC described 2 9-cylinder supercharged MAN diesel engines, each rated at 2,170 horsepower at 470 RPM. That machinery layout had to do 3 jobs at once. First, drive the submarine long distances on the surface efficiently. Second, charge the batteries. Third, remain compact enough to fit inside the hull without consuming all the space needed for fuel and torpedoes. 5. Size versus survivability. The Type IXB displaced 1,051 tons surfaced and 1,178 tons submerged. It measured 76.65 meters overall, with a beam of 6.76 meters. Those numbers gave it the volume needed for range and payload. But there was a price. A larger submarine presented a bigger target and was generally less nimble than the smaller Type 7. As the war progressed and Allied anti-submarine warfare improved, size became more dangerous. A boat optimized for long ocean patrols could never be as quick to disappear as a smaller, tighter craft. And that is the paradox at the heart of the Type IX design. To reach America, it had to be large. To survive near America, it ideally needed to be small. This seemed completely impossible. Here is why no one had solved it cleanly before. Range,
armament and survivability pull in different directions. Improve one too much, and another begins to fail. Germany's answer was not elegance. It was controlled compromise.
But here is the engineering challenge nobody had solved before. How do you create a submarine that behaves like a raider on the surface, an ambush predator underwater, and a self-contained supply system in between? The Type IXB solution worked because German engineers combined several separate ideas into one design. Step 1. Give the boat true oceanic endurance. The first requirement was simple to describe and hard to achieve: fuel capacity without losing combat function. The Type IXB's 12,000 nautical mile surface range at 10 knots made it a genuine Atlantic raider. Later, the IXC increased storage again, with an additional 43 tons of fuel, pushing range to 13,450 nautical miles at 10 knots. That was the real secret. Not raw speed, not armor, not one miracle device. Range. Without that, none of the later operational brilliance matters. Step 2. Keep the weapon load heavy enough to justify the crossing. The Type IXB's 22 torpedoes meant a commander could remain aggressive over multiple attacks instead of treating every shot as the last one available. That mattered enormously off the American coast, where shipping often moved without proper escort in the early months of 1942. A submarine that arrives with only a handful of torpedoes can score a tactical success. A submarine that arrives with 22 torpedoes can shape an entire patrol. Step 3. Use powerful direct-drive diesel machinery. Post-war technical examination of the IXC described the diesel installation in unusually clear detail. Two 9-cylinder, supercharged 4-cycle MAN diesels with saltwater cooling, each rated at 2,170 horsepower, with a 15.75-inch bore and 18.1-inch stroke. Think of the engine room like the heart of a long-distance runner. It does not just need strength, it needs endurance under stress, efficient output, and just enough reserve capacity to survive emergencies. The strength of this machinery was compact power. The weakness was heat. The same technical study noted exhaust temperatures reaching 1,022 degrees Fahrenheit, substantially higher than comparable U.S. submarine diesel figures cited in the report. Saltwater cooling also demanded careful maintenance. The engines were described as rugged, but rugged did not mean forgiving. This solved only half the problem. Step 4. Balance surface movement with underwater escape. Like other diesel-electric submarines of the era, the Type 9X fought one war on the surface and another underwater. Its submerged range was tiny compared to its surfaced endurance: 64 nautical miles at 4 knots for the Type 9B, 63 nautical miles at 4 knots for the Type 9C. Underwater, this was not a transatlantic vessel. It was a short-endurance evasion and attack machine. That distinction matters. The Type 9X was never designed to cruise across oceans submerged. It was designed to cross oceans on diesel power, then use battery power for attack positioning, crash dives, and escape. Step 5. Standardize the design for wartime production. The boat also benefited from something less dramatic but equally important: mature production. German wartime U-boat construction increasingly emphasized standardization, coordinated production schedules, and later prefabrication methods intended to reduce labor hours and speed output. The IXC, in particular, was described as a mature development intended for long transoceanic operations. So the Type 9X was not a one-off masterpiece. It was a repeatable wartime tool. The walkthrough sequence: how the engineering worked in practice. Now, let's walk through the design in real operation. 4:30 a.m. Preparation before departure.
Before a long-range patrol ever began, the boat had to be packed like a compressed machine shop, food depot, dormitory, and weapons locker. Torpedoes, food, spare parts, engine supplies, ammunition, medical items, charts, batteries, crew gear. Every kilogram competed with something else. Departure, Lorient, 23 December 1941. U-123, commanded by Reinhard Hardigan, left Lorient on 23 December 1941. This was her 7th war patrol. She would remain at sea for 49 days, returning on February 9, 1942. That date matters because once she left France, the engineering clock started. Every hour at sea meant fuel consumption, machinery wear, and growing dependence on systems that had to keep working with no shore support. Atlantic transit, engine discipline over drama. The Atlantic transit was not about cinematic combat, it was about reliability. The diesels carried the boat westward. Batteries had to be charged, fuel had to be conserved, small problems had to be fixed before they became fatal problems. And here is where the story becomes truly remarkable.
To help conceal the movement of the East Coast Attack Force, U-653 operated in the mid-Atlantic as a radio decoy, sending encrypted traffic to create the impression of activity elsewhere. This was not propulsion engineering, but it was still systems thinking. The success of the patrol depended not just on the hull, but on the larger technical network supporting the deployment. 13 January 1942, arrival on station. By 13 January, the first Drumbeat boats had reached their patrol areas. U-123 was assigned the coast between Atlantic City, New Jersey, and Long Island, New York. This is the moment where the Type 9 design proved itself. It had crossed the Atlantic and arrived as a functioning combat platform. Not exhausted, not unarmed, not merely surviving, but ready to attack. Night attacks, when American light became German targeting aid. The East Coast blackout failure gave U-boat commanders a horrifying advantage. Merchant ships could appear as black silhouettes against bright shore lighting. A submarine commander did not need perfect visibility, he needed contrast. The coast itself provided it. That was not something German engineers created, but they had built the only kind of submarine that could fully exploit it from so far away. 19 January 1942, the design under pressure. On 19 January 1942, U-123 sank Norvana at 2,677 tons, City of Atlanta at 5,269 tons, and Siltvira at 3,779 tons, while damaging Malay at 8,206 tons. Then the mission nearly collapsed. Later that day, off Oregon Inlet, the surfaced U-boat found itself in shallow water with no torpedoes left and one diesel engine out of order when Cosmos II tried to ram her. The range fell to 75 meters. If you want to understand why engineering matters in war, this is the moment. Not the design office, not the launch ceremony, not the technical manual. A boat with one failed engine, no torpedoes left, trapped in shallow water with a ship closing fast. The Germans got the engine running just in time and slowly pulled away at full speed. That scene tells you exactly what the Type 9 was built to do: remain functional when failure should already have been final. Return, Lorient, 9 February 1942. U-123 completed the patrol and returned to Lorient on 9 February 1942 with 58,972 tons credited to that patrol. Then she did it again. Her 8th patrol from 2 March to 2 May 1942 brought 64,227 tons. That is the real meaning of the Type 9 design, not just reach, repeatable reach. However, the biggest obstacle was still ahead, proving that the Type 9 concept worked not just for one famous patrol, but at operational scale. It did. Operation Paukenschlag began with fewer boats than Dönitz wanted. He had hoped for 12, received permission for 6, and ultimately launched 5 attack boats after U-502 was forced to abort because of mechanical trouble. Those 5 boats still sank 25 ships, totaling 156,939 tons in January 1942. That result was not a lucky accident. It was the product of a design that matched the mission. The Type 9 boats had the endurance to reach American waters, the torpedo load to remain dangerous after arrival, and enough survivability to escape at least some early encounters in an environment where U.S. defenses were still disorganized. The opposition reaction came slowly at first, then more effectively. Once the United States expanded blackouts, convoys, escorts, aircraft patrols, and anti-submarine coordination, the operating environment changed. The same large hull that gave the Type 9 its range also made it increasingly vulnerable as Allied anti-submarine warfare improved. So the Type 9 had a window. In that window, it was devastating. The Type IXB did not transform naval warfare because it was perfect. It transformed naval warfare because it proved that long-range submarine attack could be projected across an ocean with operational regularity. That was its real historical significance. Before this, a submarine threat off the American coast sounded remote. After Drumbeat, it was immediate. The war was no longer out there in the Atlantic convoy lanes. It was suddenly visible from American beaches. The Type IX concept also exposed the limits of the classic diesel-electric raider. It worked best when defenses were weak, escorts were sparse, and aircraft coverage was limited. As Allied air power, radar, and anti-submarine tactics improved, the old model of a submarine traveling mainly on the surface and diving when threatened became far riskier. So the Type IXB stands at an important turning point. It was one of the clearest expressions of the early war German long-range diesel raider concept, a design philosophy built around endurance, torpedo load, and surface mobility. And here is where the story becomes truly remarkable. The very success of boats like U-123 helped force the Allies to change faster. Convoys tightened, coastal blackouts expanded, air patrols improved. The submarine war became more technical, more lethal, and far less forgiving. In that sense, the Type IXB did more than sink ships. It accelerated the evolution of anti-submarine warfare itself.
The achievement can be summarized in one sentence. German engineers built a submarine family capable of carrying 22 torpedoes across the Atlantic, operating off the American coast and returning to base, with the Type IXB rated for 12,000 nautical miles of surfaced range at 10 knots. That legacy still matters now. The next time you watch a modern documentary about submarines operating far from home waters, you are seeing the same design question that shaped the Type IX. How do you combine range, stealth, payload, endurance, and survivability in one hull? Today, the answers are different. Nuclear propulsion removed many range limits. Sonar became far more powerful. Quieting technology changed everything. Sensors, fire control, and underwater endurance all moved into a different world. But the trade-off is still the same. More reach often means more size. More size often means more risk. And every submarine designer still lives inside that equation. Now think about the what-if moment. If the Type IXB had carried less fuel, U-123 might never have stayed on station long enough to matter. If it had carried fewer torpedoes, the Atlantic crossing would have produced less strategic effect.
And if that disabled diesel had not restarted off Oregon Inlet with Cosmos II only 75 meters away, one of the most famous patrols of the Atlantic War might have ended right there in shallow water. That is the deeper lesson. History does not always turn on the largest fleet or the loudest victory. Sometimes it turns on whether engineers can make an impossible machine work just long enough, far enough, and reliably enough to change the map of a war. This channel explores the engineering secrets that changed history. If you want more hidden design stories from naval warfare and the space race, subscribe and turn on notifications. And tell me in the comments. Thanks for watching.